The reason why we bring up the periodic table of the elements, one, we're on the third floor, hallway, and we have a periodic table of the elements, just sort of right there. We're also a major that likes to talk about systems, and as a major that likes to talk about systems, we know that systems like to and can be described by accepting as input energy, and as a system, there could be a specific system, a specific, not the ocean Pacific, energy. There could be a specific amount of energy that pops back out. And for those of you who were with us this past fall, just a little while ago, we had our physics class. We talked about energy for the entire time. And that's why we include an energy course inside physics, it's inside ISBT, because we talk about energy as well as systems. Let me get a little here. As a systems major, we also talk about information, input and output. So, a year, well, actually not a year from, gosh, it's almost here. This coming fall, we're going to spend an entire semester talking about information. We're talking about how to measure it, how to transfer it, and things like that. We've already talked about energy again. We'll continue to talk about it in our physics class. But we'll be talking about information in our instrumentation and measurement class, and then literally a year from now, we're going to be talking about our big three. Our third, materials. So as an ISBT student and as an ISBT major, in addition to talking about systems, both physical systems and technology systems and business systems, we recognize that energy, information, and material, or materials, are important to all of those things. So at any one time, we could stop what we're talking about and saying, pause. Let's make sure we understand what energy is going on here. Let's talk physics for a while. Pause. Let's talk about information, measurements, and transducers, and calibration, and computers. And pause. Let's talk about materials. Okay. So we started talking about materials on Wednesday because I think it is sort of important for us to figure out, or at least get an analogy or some sort of basis as to how in the world does this thing called a diode actually behave? What makes it do what it do? Okay. If it's an energy thing, then we have to be concerned about what energy environment it is in. If it's an information thing, then we have to know how to talk to it correctly and understand what it's saying. But if it's a material thing, we have to understand what goes into it, okay, and how do the materials behave. Of course, as you guys know, it's always a combination of all three. However, the majority of the explanation as to why diodes do what they do is because of the materials they are made out of and how they are constructed. It's a materials technology. It's a materials thing. Okay. So on Wednesday, I attempted to draw a little schematic, and again, not perfectly correct, but close to it. That's sort of the outline of the periodic table of the elements without those last two on the bottom. And we said there is, in fact, this is usually wider, but still, I'll get close. Usually there's a little stair-step thing. I even have a red pen that should be on it in red. And that red pen separates that periodic table not in half, obviously not in half. In fact, the majority of all of the elements are sort of on this side of that goofy line. And there's a couple over here, majority-wise, are over here. And we said, if you do enough experimentation, these elements over here, when they bond, or when they get next to another atom or another element, they donate electrons. They have so this is sort of a push thing. We're talking about physics, and yes, energy's involved. We talk about forces, pushing and pulling. Those elements tend to push away their electrons when they get next to another element. These guys over here tend to accept electrons or, of course, pull. Okay, so again, I don't want to summarize all of last semester into forces and Newton and push and pull, but yeah, we could probably do that. It was just all about pushing and pulling stuff. That's what we did with energy. So we're still talking this push and pull story, okay? I'm sorry? Oh my gosh, we're getting there. Good morning, man. How are you?
Don't they not?
They don't give. Yeah. They're like honey badgers. They just sort of hang out. 0 electrons given. Yeah, exactly. We're going to talk about that in a second. So yeah, thank you for pointing out the noble gases. In fact, you'll notice, red pen-wise, on our periodic table, they're even written in red or pink or whatever, puce or whatever. No, puce is a yellow, isn't it?
I'm not the right person.
Oh, I'm not the color expert. I think puce is a yellow.
Like a pink.
It's like a magenta, like a pinky thing over there. Yeah, exactly. Yeah, the noble gases are their own little party. So yeah, we'll talk about those in a second. It's important to realize that when we build stuff out of those stuff, the very fact of how they behave, and how they act, and what they do is important. Otherwise, they'll fall apart. Okay. So yeah, these guys over here tend to donate electrons. Okay. So, RJ, would you mind playing along? Fantastic. Would you mind being a element on this area of it's kindergarten, on this area of the periodic table? Okay. And we're going to represent electrons by these really fantastic, expensive markers. Okay. There you go. And I'm also going to be an element that wants to say, bless you, electrons, okay? So I'm like, yeah, this is extra. I don't want this. Again, we talked about why they do that. They, energy-wise, they would be much lower energy if they got rid of those extra 1 or 2 pesky electrons and went back to a full shell. You have the same condition that I do, right? You'd be much happier, you'd be lower energy if you get rid of that damn marker, okay? So here I am, and I'm on that side. I want to get rid of this guy. Gosh, I need someone to give this marker. Here, take this marker. Okay. Now, how happy are you? You're not yourself anymore, and you want to get rid of your marker too, right? So what are you going to do? Yeah. Well, that was quick. No. I don't want it. I don't want it. No, thanks. So we're going to do this all day. Okay. No, you take it. No, you take it. Now, if we take this fast enough, if we do this fast enough and you take a video of us and pictures, you're going to see us like this all day. Like, that's what they look like when they're done. But it's not that we're holding on to it. We're sort of pushing it. We're both pushing at the same time. Okay? I don't want it. No, I don't. No, really, it's yours. No, seriously, it's you. No, it's all you. Here you go. We're gonna spend eternity doing this. Okay, back and forth. Thank you for playing along. Okay, those guys are called metals. That's what metals do with electrons. Okay, they would prefer to get rid of them, but if they donate their electron to another metal, the metal's like, well, wait a minute, I wanted to get rid of this guy, now I have an extra, take it back, okay? If we're all playing the game, and we all have a marker we want to get rid of, we could just do the around the room. Here, well, you start playing hot potato, no, you take it, no, you take it, no, you take it, no, you take it. Of course, that's called conduction, okay? That's how we get one marker around the room. Everybody just sort of passes along. And says, shit, now I have 2, I only want 1, and off it goes, okay? That's what happens when these types of materials get an extra electron. Well, first of all, they want to donate their electron to begin with, but when they're given an extra electron, they really want to get rid of it. Okay. So if we take, oh gosh, what's a metal? I think it's right about there. This guy is a common one that we use. Anybody familiar with copper? Yeah, copper wire. Right next to it is zinc and nickel. I don't memorize this, I'm just reading it off the chart. Right below copper is silver, and below, thankfully they have their names, I don't memorize them. And then gold underneath that. So Those are all metals, and you can make wires out of those things. And the way it works is when you have copper, a copper atom, if you will, next to a copper atom, they don't fall apart. Copper doesn't just shatter into thousands of pieces of glass. Copper's a thing, and it stays together. The reason why it stays together is it's so busy giving electrons back and forth. Okay, it happens so quickly. That exchange happens so quickly that if you looked at it, you took a picture of it, you would see them sort of connected by their exchange. They're pushing. They're not trying to push so hard they're exploding, but it's sort of this network of electrons happening. Okay, so that's one way to envision what happens. And the way this works is if this is the electron with its own electron, this electron with its own electron, this copper with its own electron, and if I were to convince this electron to take this one, well, then it would give that guy and give this guy, and then it would pop up the other side. That's what we call conduction. Okay, so the analogy, electron-wise, is very similar to the analogy of a garden hose. If we already have water droplets inside of here, and I force another water droplet, they sort of all move over until one droplet falls out. That's sort of our picture, that's our analogy of how electrons get conducted inside a wire. These guys are metals. These guys, the ones that accept, again, I wasn't around when they named these things. You think it'd be a cooler name. They're the ones that aren't the metals. They're honestly called non-metals. I don't know why. They could have organized and got a better name, I'm thinking. Metals and non-metals. There's not many of them. They're just up in that corner over there. Okay. And one of the non-metals happens to be carbon. Carbon is a big non-metal these days. Hydrogen's goofy. Hydrogen is ambivalent. It can behave as a metal or a non-metal, it turns out. It can lose one electron and become a no electron ion, or it can gain an electron and then look like helium and fill its shell. So it goes either way over there. But usually we have compounds of carbon and hydrogen together. I think they're called hydrocarbons. Yeah, hydrocarbons. And hydrocarbons are us. Those are biomolecules. I'm made out of hydrocarbons. My skin, my hair, my fur, my shirt, they're all hydrocarbons. They are non-metals, okay? Non-metals accept. So when we take two non-metals, let's say, for instance, a copper, that's Cu, a carbon and a hydrogen, okay? And we're going to have the hydrogen act like a non-metal this time. Can you play it on again, please? There you go. You already have one electron, but you'd love to have two. Okay? You'd be happier. Your energy would be better if you had an extra electron. And me too. I'd also be better if I had an extra electron. Okay? So I'm just like, hey, nice electron. Can I see that? And you're like, yo, you have to hold on to it because you don't give them up, right? So now we're stuck again, right? But this time we're pooling. We're both pooling. And well, even though we're pooling, thank you, we're bonded together. We call that not pooling because pooling is too antagonistic in our politically correct world. We call it sharing. They're sharing the electron. Isn't that nice? In fact, they're like cohabitating together. They're cohesive. We call them covalent. The outer shell electron is called a valence shell, so they're covalent. So what happens here with the non-metals is these guys are sort of sharing, I didn't mean to draw that as a double bond, but they're sharing their electrons, and they're doing so permanently. They're bonded together, they're sort of stuck together. But what happens is they're sort of pooling on these electrons, even though in organic chemistry, one line equals a bond. One line is actually two electrons. It takes two electrons to bond, so it's sort of a double story here. So metals over here would like to get rid of the electrons. They just pass them along. You give them an extra one, pops up the other side. Non-metals, if you go ahead and give them an electron, they're like, no, I'm good. I'm already sharing with my friend over here. They sort of ignore you. They don't conduct at all. Not at all. They're very good insulators. Okay, so that's why. If you must grab some wiring, you might want to put on some oven mitts or some heavy gloves. Usually things that are good conductors of electrons are also good conductors of heat. So that's why you put on oven mitts when you're getting the cookies out of the oven, because you can touch it with your gloves on because the heat won't conduct, because you're using covalent nonmetals to do things. So that's one. This is one version of what's going on. This is two versions of what's going on. And then, of course, we have, what about a metal and a non-metal getting together? You need to pick a metal and a non-metal. What? Potassium. Just something simple like that. Like potassium and fluorine, something like that. Okay. Potassium, metal, would like to get rid of its electron. Fluorine would love to get an electron. Okay? So you play potassium, you have electron you want to get rid of, and I'm fluorine. Okay? Hey, are you using that? Okay, can I have it? I can have it. I can have it. Okay? I permanently have it. Only one problem. I now, honest to God, have one extra electron. What happens to my net charge when I have one extra electron? I'm not sharing it anymore. I have one extra electron. I'm more negative by one whole one. You're missing an electron. What about your charge? In fact, positive one. Okay. What happens when you take? I won't cuddle with you. What happens when you take a negative charge and a positive charge and they get close? They're stuck. Okay. So what happens is these types of materials, when you take a total positive and a total negative, because they transferred their electrons, they're just stuck together because of the attraction between positive and negative, and they're very, very difficult to pull back on. They don't stretch. They don't go, you can take a sledgehammer and smack them apart, okay? And the types of materials, well, this guy right here we call a covalent bond. This guy we call an ionic bond. I mean the bond word, because they're ions now. And this guy, who was making these words up? A metallic bond. Not Metallica, not the band, but metallic. Okay? Metals bond using metallic bonds. Wow, who would have thought? What a great idea. Covalent, ionic, metallic. These guys pass their electrons very, very quickly, highly conductive. These guys don't pass their electrons. They're stuck together because they're sharing, and they usually don't accept any additional electrons. These guys, it all depends. They can and they can't. Usually these guys aren't conductive. Usually these guys don't bother with extra electrons because they're ions. However, if you've ever heard of superconductors, they're usually made out of these materials. So we have examples of totally crappy conductor and the best conductor we've ever had. It all depends on how they're actually put together. Metallic bonds, metals, covalent bonds, non-metals, but non-metals is really a crappy name. They're better described by the class of materials we call polymers, plastics. Okay, so that water bottle there is a plastic. That's a polymer. That's being held by this type of bonds. Ionic. Is ceramic and glass materials. So your glass jar is an ionic compound. Same thing with the glass over there and the glass in this window. The reason why I'm bringing this all up is because next year, in this class materials, we're going to be talking about all the cool things you can make with those different materials, okay? Those different classes. There's only two things that make things up. There's either metals or there's non-metals, and then you can combine them, metal with a metal, non-metal with a non-metal, or you can do the both, okay? And then, yeah, we get to the noble gases. Back in the day, they used the word noble referring to kings and aristocracy, because the kings and the aristocracy and the queens and the nobles and the princes and the princesses, again, they didn't give a flip. And they definitely didn't mix with the commoners. They were off by themselves. Okay? So the noble gases, the one in the last column over there, the heliums, the neons, the argons, the kryptons, the xenons, and the radons, they are not very reactive at all. They're already cool. I'm good. I don't need an electron. So we usually don't talk about molecules with those guys. So they're just sort of extra. So what about our story of the diode? Okay? Remember, our diode can be put in this direction in the circuit, positive and negative, and current flows, or it can be put in this direction of the circuit, positive, negative, and current doesn't flow. Okay? We need to, by virtue of which way it's pointing, have it be a fairly good conductor or a fairly crappy conductor. How do we do that? Well, I guess we could make it out of metal, which is a fairly good conductor, and then when we don't want it, we can make it out of a non-metal, which is a fairly crappy conductor. That won't work. We can't go ahead and actually change what it's made out of. I know what, maybe we can make one side, one end, out of the conductor, and the other end, no, that won't work either, because they have to go back and forth. We're not going to solve it standing here. Someone solved it. The scientists solved it. They said, what if we use a material that's sort of in the middle, and if we subtly sort of change its, here's the key word we talk about all week, if we subtly change its environment, then we can convince it to act like a metal and conduct, or we can convince it to act like a non-metal and be an insulator. But by virtue of what environment it is in. If we just get it somewhere in the middle, okay, and then if we, whatever we put over here as an input and an output, positive on this side, negative on that side, or flipping it around, negative on the arrow side and positive on the other side, maybe we can convince it to behave differently based on its environment. Well, to do that, we're going to need a conductor. Well, no, actually we're going to need an insulator. We're going to need something in the middle, okay? So they invented a word for those materials in the middle that aren't the best conductors, but they're not the worst conductors. You know what they're called? The transition metals are fantastic. I like that. But even closer. Conductor over here. And non-conductor over here. Now you said metal. And non-metal. In the middle you said semi. Yeah, we can use a semi-metal. Semi-metal is a popular word. There's even a more popular word. And that's a semiconductor. A semiconductor. Semiconductor, okay? A material that is in the middle, and by virtue of its environment, it could be a pretty good conductor or a pretty crappy conductor, depending on how we convince it to go the other way. Okay? The semiconductors, is an entire region of the periodic table. Again, it's not half and half. Metals, good conductors. This direction, awesome, super fantastic metals. This area, non-conductors, they're covalents. The more you go this way, more non-conductive. Somewhere in between, which happens to be somewhere along this line, okay? Sometimes we call them semi-metals. We're going to pick one, looking at our chart over there. We need something along that line. Yeah, it turns out that it's silicon, okay? So we've tried, we use arsenic, we use tellurium, we use antimony, we use boron. Boron's fun. It turns out that silicon, and it is, it's element 14. And if we were to count these guys, there's 2 rows over here, 1, 2, and then there's 3, 4, 5, 6, 7, and then there's the 8 guys, the honey badgers that don't really care. Okay? Silicon's in what group? 1, 2, 4. In fact, if I were to draw, probably right there, right? All right. So if column 1 is the most metallic and column 8 is the most non-metallic, how about 4 for being in the middle? Yeah, damn straight. It's 4. Okay? 4. So if we have 4, if we make 4 a 5, then it's on the non-side. If we make that 4 a 3, it's on the metal side. There's a way we can convince that 4 to be a 5 or a 3 by virtue of its environment. Okay? Again, this is not me just describing a fiction novel. This is like years and years and years of research and discovery. And holy crap, this works out really well. What a great idea. Yeah, it's pretty much called the 20th century, or the last 100 years of working with silicon. Anybody know where we do a lot of this stuff in the United States? California. Do you know what its nickname is?
Silicon Valley.
Silicon Valley, right, exactly. That's why. Yes, there's a lot of silicon there, and yes, there's a lot of silicon all around the world. Where would you find silicon if you needed to go, hey look, there's some silicon? Anybody know where you'd find it?
Probably in the mountains.
Mountains is cool. Turns out that the #1 place for silicon, sand, beach sand. Beach sand is silicon. You just think, hey, let's go to the beach, but yeah, it's everywhere. It's rocks. Okay, so Silicon Valley out in California is where a lot of the research and entrepreneurial little tiny groups said, hey, let's start working with silicon and let's see if we can convince it to be a conductor or a non-conductor, and we can do all kinds of cool things like the diode. That's pretty cool. So here is our silicon. Okay, silicone is different. Silicone is actually silicon, the element, behaving like a non-metal and being bonded with oxygen. It's actually a polymer. That's like a silicone rubber. But silicon is the element. We said it was element 14, but it is group 4 on the 4th column. 1, 2, 3, 4. And because we know how these things work in the periodic table, the elements over here have a full shell. This is one model. There's the nucleus. And then there's 1 electron sort of all by itself in its outer shell. That's this guy. This is 2 outer shell electrons. This is 3. This is 4. Silicon has 4 electrons in its outer shell. Sort of like here's silicon in the nucleus. And then around here in its last shell is 1, 2, 3, 4. Okay? So I mentioned before, the scientists, this is not me making this up, the scientists said it'd be great, silicon as itself is an okay conductor. It's a semiconductor, a little bit or not a bit. What if we were able to give silicon an extra electron? Of course, it would make it an ion, but then it would have 5 and it would act more like a non-metal. Or what if we were able to take away an electron? Of course, it would be an ion, and only give it 3. Only have it 3. It would be more like a metal. Okay? So the engineers and the entrepreneurs and the designers said, hey, wait a minute. If we have an entire collection of silicon, here's silicon, 1 there, and 1 there, and 1 there. I'm going to put 5 of these guys together. Okay? Each of these guys have 4, I'm going to use the number 4. Each of these guys have the number 4 electrons next to them. Instead of convincing 1 or several or all of those silicons, let's make them metal first. Instead of taking away an electron from each of them and then making this thing this huge positively charged thing, what if we just replace one of these silicons with a different element that only has 3? Again, according to the electrons, it would just see 4, 4, 4. Holy crap, there's only 3 there. Okay, but we'll just change the actual material itself. So what we're going to do is we're going to go over to the semi-metals, and we're going to go to column 3. Aluminum. Aluminum's a fantastic metal. It's not playing ball. Aluminum's great. However, right below that, gallium and indium, Ga and In, they're pretty cool. They're pretty good semiconductors. Okay. So what we're going to do is let's go ahead and replace this guy with an element or an atom of gallium. Okay. In fact, let's do that a couple of times. Let's go ahead and maybe replace this guy over here. That only has 3. Okay. Now, of course, we're doing this in a giant block of this stuff, not just every other one that I've seen on my little board here. But now, according to an electron, of course, that's trying to jump, there's now a space where there's a missing electron. It's only 3. So maybe there's room for an extra electron because it sort of act like the silicon. Okay, so what we're doing is we're making the overall system a little more friendly to electrons because it looks like they're missing electron, but we're missing electrons because we've changed the atom, not by stealing one. Because if we steal one, then it becomes ionized, and all bets are off, because then now it starts repelling back and forth. This is still neutral. So we're going to put a small percentage of gallium, or another one, indium, in with the silicon while it's molten. I mean, literally like making chocolate chip cookies. We're going to make it homogeneous, and then we're going to let it freeze. Okay? When we're done, we're going to get this crystal, this block of silicon gallium semiconductor. Okay? I didn't make this up. It's called doping. There was a famous bicyclist, Lance Armstrong. Did he get in trouble for doping?
Yeah.
So what do we use the word doping for? Like he took extra chemicals to make himself better?
Yeah.
That's where this comes from, this doping. Again, this predates Lance Armstrong, okay?
Yeah.
The scientists doped the silicon with extra chemicals, with gallium, to make it more metallic, to have it have less electron. This is gallium-doped silicon semiconductor. Sure, that's not on the test. I'm not going to ask you this stuff. I just want you guys to realize where it's there. And we're going to constantly, through all 4 years of being an institute major, look at cool inventions and innovations like, wow, that sort of makes sense. And when you're done, we now have this entire industry called the semiconductor industry. That's how all of our cell phones work. Based on that. If it works for doping with gallium to make this less, then maybe it will work to dope with another material and make more electrons. Okay, so this guy's missing electrons. So if it were actually missing it, it would be positive. So they call this guy p-type because it's positive type. It's missing electrons. It behaves more metallic, like a metal, because it's missing electrons. We're getting back to this guy in a second. Let's do this again. Silicon, missing, silicon, missing, silicon. Let's dope the silicon with a different semiconductor that has 5 electrons. Let's give it an extra electron, make it more non-metal, make it more of an insulator without actually making it an ion. So we used gallium and indium before. How about arsenic and antimony? Okay, As and Sb. Let's use arsenic. Arsenic's a popular semiconductor. Has anybody had arsenic for lunch recently? Anybody know anything, a fun fact about arsenic? It's really poisonous. Yeah. So yeah, when people hear that you're using a laptop, that has arsenic in it. It really does. But it has atoms of arsenic, and they're inside these crystals of semiconductors. Even if you lick the chips, you're not going to eat it. Okay? But if someone were to literally take arsenic, the metal, and put shavings into your lunch, Alfred Hitchcock made millions of dollars by people getting poisoned by arsenic. It's a very popular poison. So don't do that. Don't eat arsenic.
How do you make money doing that?
I can make money. What?
How do you make money?
Oh, he's an author. He wrote almost.
So he told people about it.
Well, he wrote fictitious horror stories and murder mysteries, and everybody was poisoned by arsenic. It was like the #1 way to kill people. And Yeah, so now in 2016, the number one lighting people was like stabbing them with an icicle so that it like melts. That's a popular. If you watch CSI, yeah, that's a popular way to go. Arsenic, for whatever, in the 40s, 50s, arsenic was the way to go. It was like the popular way to be. Anyway, so yeah, if you're working for a semiconductor company and you are making, well, if this is called P-type, what are we going to call this guy? Of course we are. I can spell it. This is a 4, this is a 5, this is a 4, this is a 5, this is a 4. Now we have extra electrons. It's going to be more negative, if you will. It has extra electrons. And yeah, we're going to call it N-type. So now we have P-type and N-type semiconductor, in addition to having regular old silicon in the middle. Okay? So who cares? This is great. Fantastic explanation, even though it was a crappy explanation. How does that help us with our diode? Well, here's the deal. Instead of talking about that picture, let me grab the mark that works. That's what works. We're physically going to make a little tiny diode, and half of it will be P-type, and the other half will be N-type. Okay? What I'm going to do is I'm going to put the N-type over here, and I'm going to put the P-type over there. Okay? The front half will be P, and the back half will be N. And this guy's positive, and this guy's negative. Okay? Just like before. Okay? With the P close to the positive and the N closest to the negative, that's what it looks like. That's the. If I could actually draw an N and a P, this is the P side. This is the N side for a PN type diode. I don't see how that helps us. Okay. Remember, the N type has extra electrons, if you will. So the way I'm going to draw this is I'm going to draw those extra electrons. I'm going to use the marker that works. Okay, I'm going to draw those, just the extra electrons, and not all this other jazz. Yeah, you can envision in your mind's eye, there's silicons and there's arsenics. I'm just going to draw the extra electrons, okay? On this side, here's the P. We're missing electrons. And because I had eggs for breakfast, I'm going to draw this as an empty egg crate. There's parking spaces, there's slots full of electrons, but they're missing. But there's room for the electrons to go, okay? So the P-type has extra places for electrons. It's missing. They could fit some extra electrons if they had any. And over here, these guys have extra electrons. Okay? Here's our negative. Here's our positive. I keep on mentioning and ask you guys to think about current as being going from positive to negative. Because it makes sense, I guess, for things to fall down. But as physicists, we know that's not true. That's a made-up story. There is no positive charge. It's not protonics. There actually is an area of research called protonics. We're talking about electronics. We're talking about electrons flowing. So all that stuff about current flows from positive to negative, that's still true, but let's put that fake story on hold. Let's think about the actual electrons. This is what we're talking about, right? Negative pole of our power supply is negative because it has a whole bunch of high pressure electrons, high voltage electrons. Positive is missing electrons. Okay, it has it doesn't have enough electrons, which makes it positive. So we put this diode in the circuit. We turn it on, and all of a sudden we have this huge push of electrons. This is a cartoon. What happens? This electron gets shoved into that end of the diode, just like a wire. Okay? What happens to the rest of these electrons when we shove an extra electron in here? Same thing with the wire. Bump, ba-dum, 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 ba-dum. Oh, look, there's a nice space for an extra electron. Okay? And then we just keep on shoving. Dun, 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 over to here, over to here, over to here. After this fills up, okay, out comes like, oh, wow, fantastic. It conducts just like a wire. So this is a diode picture. Remember, our wire picture looks like this. This is our wire cartoon. A wire cartoon already has the electrons filled up. And when we go ahead and put one electron in, the other one pops out. So when this material is in this orientation and we turn on the voltage, there's some time. The time is almost instantaneous. The rest of the material fills up and then it flows. And then once the diode is happy, once the circuit has settled down, this just flows current all day. Okay? I'm sorry?
From the right to the left.
In this picture, we're looking at the flow of electrons, not the flow of positive current I. So even though we're sort of visualizing in our mind's eye the electrons going from negative to positive because they're falling up, this is what we mean, the current flows. If they're flowing up, it comes back down. It's confusing as hell. I'd rather just, as a physicist, stay with electrons and say, guys, it's electronics, get over it. But everybody likes to see things fall down. Okay? So, great, what a fantastic way to think about this. What if we switch this guy around?
Wouldn't work.
Diode. Let's put the P over here. Let's put the N over here. Here's negative. Here's positive. This is a push. Oh. Bunch of electrons. We turn it on, okay? When we, this guy's this way, it's going backwards. When we turn it on, these electrons, yes, it's true that these guys, there's a parking space, if you will, and there's a space over here, but it turns out that this movement from there into there doesn't happen by virtue of how they've adjusted the formula. Because for this guy to jump into there, this extra sparking space, this guy would have to get an extra electron. It would have to be ionized. And we're not talking about giving it an extra negative charge. We're just talking about these guys just sort of shifting their electrons that are over here. They've adjusted it. Inside the material, this does happen where it fills the empty spaces. This guy is designed that electrons from the outside won't fill it up. So it's as if one picture I sort of had in my mind is sort of this bridge, this chasm. Here's the electrons. There's nothing to get the electrons across. They're just gap. It's as if the circuit is open, again with the drawbridge and the closed drawbridge. Okay? No current flows. Here's the current, positive, negative. Here's this guy. No current flows this way because no electrons flow that way. So the diode does not allow things to flow in this direction. You could physically pick it and turn it around and it will flow. What normally happens inside a circuit is that we change the direction of positive and negative. And when we flip the positive and negative, then it flows the opposite direction. Okay. We have 2 more minutes. There's one more explanation. Again, this is just cartoons, so we're not solving actual physics equations and math equations. Positive, negative, P, N, this guy, this guy. these extra little flaps on this diode. You guys remember what the extra little flaps on the diode meant? It's a Zener diode. Remember why a Zener diode is different than a regular diode? What's the behavior of a Zener diode? Do you recall? We put it in backwards in the lab, and then we cranked up the push. And nothing happened, nothing happened, nothing happened, nothing happened. And then once we reached a certain amount of push, then something did happen.
They only activate if you have a certain amount
A push.
push.
Okay. So the Zener diode, using our cartoon, is still made out of P and N, but the reason why a Zener diode is made differently than a regular diode is the concentration of the N and P is different. It just so happens that this is designed so that when this electron does push in here, it will accept it. But it only accepts it after you push really kind of hard. Okay? A little push, it'll ignore it, just like a regular diode. Zener diode, if you push hard enough, then okay, I'm just filling up. I'm getting close, watch out. And then after you reach the Zener diode, they call it the breakdown potential, then this just turns into a wire, and it opens up. Okay, so a Zener diode, it holds back until you push hard enough. And then once you push hard enough, things start to flow. Okay? Fantastic. This was not meant to be 4 years of metallurgical engineering, but it was. This is a lot of different concepts. If we wanted to do this for real, and we wanted to work for a semiconductor company, and we wanted to develop Zener diodes and regular diodes, we have a lot of math behind this, but this is not fake. This is not the kindergarten version. This is our understanding as scientists of what's going on. What makes this happen in reality is real science, real engineering, real computers, and real mathematics to get the formula right. But this is exactly what's happening. We have a solid state piece of semiconductor, but if we make the recipe just right, it's actually a pretty simple little thing. And yeah, this also gets you a Nobel Prize. So had we done this in the 40s, we'd all be eligible for a Nobel Prize. By the way, yeah, it's one of those things where you didn't know before, and now you do. Like, that's easy, but no one knew before. Which is kind of cool. Fantastic. Thanks, guys, for week 4. We'll be back on Monday. Then. much.